Hey everyone. Have you ever stopped to wonder how a computer can possibly understand something as human as poetry, or translate tricky dialects, or even write its own code? Well, it's not magic, it's math. So today, we're going to pull back the curtain on the surprising and honestly pretty elegant mathematics that let machines get a handle on the messy, beautiful world of our language. All right, let's just jump right in with a famous little puzzle that looks, well, impossible. How on earth can a computer do this kind of word algebra? By the time we're done here, you'll see exactly how it solves this riddle, all by treating words like they're points on a map. So, to really get to the bottom of this, we're not starting in some fancy university lab. Nope. We're going to follow a real-world developer who's facing a classic problem. They had huge ambitions, but a pretty small budget. You see, as developer Puneet Arora explains it, his team had a tough job: build a really complex translation tool for different dialects. They just couldn't afford to build a giant AI model from the ground up. So they had to get scrappy and figure out a clever way to fuse existing AI tools together. And this whole situation led them to this massive question, one that's really at the heart of AI today. Could the clean, predictable, black and white rules of math actually unlock all the shades of gray in human language? Or was this just a dangerous shortcut, trying to jam a messy human problem into a neat little mathematical box? Their journey, and ours, kicks off with one of the most fundamental ideas in AI language processing, something called word embeddings. Okay, think of it like this. Imagine a giant, invisible map. Every single word you can think of is given a specific coordinate in this huge multidimensional space. So happy is located right near joyful, car is just down the road from truck, and king is super close to queen. All of a sudden, language isn't just a jumble of words anymore. It's a literal map of meaning that a computer can actually navigate. So what's in this toolkit? I mean, once words are just points on a map, what can we actually do with them? Well, it turns out you can use some surprisingly simple math to perform some incredibly powerful linguistic tricks. First up, we've got plain old addition. But in this world, adding two word vectors together is basically like combining two concepts to create a brand new one. And get this, here's a perfect real-world example. If you take the vector for the Hindi word for knowledge, and you just add the vector for home, the point you land on is right next to the vector for school. The math, it literally understands the concept. It's wild. Subtraction is just as powerful, but you gotta think about it a little differently. It's not really about removing a word. It's about isolating a relationship. It's like finding the path between two ideas. So, for example, the path from man to woman is basically the concept of gender. And this is how we crack that puzzle from the very beginning. Check it out. If you take the vector for king and you subtract the vector for man, what you're left with is a new vector that basically just means royalty. That's it. Then you just add that royalty vector to woman, and voila, you land right on queen. Okay, so what if you don't want to add or subtract? What if you just want to know how similar two words are? For that, we use something called cosine similarity. All it does is measure the angle between two word vectors. If that angle is really small, it means they're pointing in almost the exact same direction on our map, which means they're semantically super close. And this is a total game changer for that developer's translation problem. See, a word in a local dialect like Mora for my might not even be in a standard dictionary. But by finding the Hindi word with the highest cosine similarity, the model can correctly figure out, oh, you mean Mera, because on that big map of meaning, they're basically pointing the same way. So, with all these amazing tools, it really feels like we've just solved language with high school math, right? Well, this is the exact moment our developer realized that if you rely only on the numbers, you can walk straight into what you might call a mathematical mirage. Here's the trap, the big one. It's assuming that just because two words are close on the map, they must mean the same thing. But that map, it can be really deceiving. So here's trap number one. In math class, A plus B is always the same as B plus A. But in language, oh man, order is everything. Tiger ate man and man ate tiger use the exact same words, but swapping them creates a wildly different story. A simple mathematical average would see those two sentences as identical. And then you've got this one, the polysemy trap. Math wants to give every word one and only one address on the map. But that's just not how we talk. Human language is full of words with multiple meanings. The Hindi word tir, for example, can mean arrow or it can mean riverbank. So its single vector is stuck being a useless average of both meanings, landing it in this kind of semantic no man's land that isn't really accurate for either one. So you can see the problem, right? Faced with all these weird linguistic traps, the developer realized that just mixing different AI models together, like stirring two pots of paint, was never going to work. The intuitive idea, the one you might have first, is to just average two different language models to get the best of both worlds, a supermodel. But the reality is that's a total disaster. Each model has its own internal map, and the dimensions on those maps mean different things. Averaging them is literally like trying to average a map of Mumbai and a map of Delhi. The coordinates become meaningless, pure noise, because the maps aren't aligned. The much smarter solution, the winning strategy, was something called concatenation. So instead of averaging and just blurring all the information together, they stacked the vectors from each model side by side. This creates a new, richer, higher dimensional vector that actually preserves the unique wisdom of both models. It lets the AI learn which map to read for which specific task. And this, right here, is the key takeaway, all laid out. If you want to get the gist of a sentence, yeah, you can average the words, but within one model. If you just need more vocabulary, you use a fallback system. But if you want to combine the actual strengths of two different models, you have to concatenate. It's all about using the right mathematical tool for the linguistic job. This developer's journey really shows us something profound. AI is absolutely built on the beautiful, logical engine of mathematics. But language itself, it isn't always logical. It's messy, it's contextual, it's deeply human. And the future of AI really depends on knowing not just how to use the math, but on having the wisdom to know when that math is leading us to an elegant solution and when it's just creating a mirage.